Good afternoon students. This video is for class 9 physics and today's topic is change in momentum. So, change in momentum here. Change in momentum is denoted by del P equals to del mv. That means this del, the small triangle here is called del or delta before a quantity, any quantity, like if it is before, if there is a small change in force, if there is before mass, there is small change in mass, if there is del is in front of v, it is small change in velocity. So I hope you understood. The del represents small change, right? So if you want to change momentum, or if momentum changes by itself, right, because of some force and some energy, then what happens is this change can occur because of the change in momentum, change in mass or change in velocity, because momentum was p was equal to mv, right? So del P, that is small change in momentum, should also be equal to del mv. I hope you understood this, right? So P should be equals to m into v. If P is equals to m into v, then del P should be equals to del m into v. I hope you understood till here. So here the symbol del represents small change. The change in the product mv can either be due to the change in the mass or due to the change in velocity. So this del, if you see here, del m v in the bracket, del m v is in the bracket. This change in the product of mass and velocity can be because of the change in mass or change in velocity or both, right? Because if mass also changes, the product will change. That means if suppose the mass is 50 and the velocity is 20, so it will come 100. Suppose instead of 50 we are taking 25, the product will not remain 100, right? It will become less. So that means change in the product of mass and velocity can be due to the change in mass or due to the change in velocity. I hope you understood this. So the change in the product of mv can be either due to the change in mass or due to the velocity or due to both. The mass m and velocity v, if mass remains constant, right, if the mass does not change, then change in momentum is due to the change in velocity alone, which generally happens, right? Because suppose you push a chair, right, the chair was at rest, therefore the momentum of the chair should be 0 because the velocity is 0, right? And you start pushing the chair, then what will happen? It will gain some velocity, hence it will have some momentum also. Will the mass of chair change if it does not break? It will not change. So change in momentum is just because of the change in velocity in that case. Thus from equation 3.2, right, for constant mass the change in momentum should be del P equals to del mv, which is equals to m del v. Why this del is not in front of m, right? Because mass generally does not change, right? I hope you understood here. If you haven't understood, please write in the comment section. Okay, del P equals to del mv. This del cannot come in front of m because m did not change during the change in momentum, right? It did not break. So we are talking about the intact object, right? I hope you understood till here. The next thing is, in case of atomic particles, very small particles moving with the velocity comparable to the velocity of light, okay, this is the highest velocity an object can gain, right, which is 3 into 10 to the power 8 meter per second. No velocity is more than this. It was observed that the mass of the particle does not remain constant. That means if it is moving with a velocity near to this value, okay, any object if it moves with the velocity near to this value, then the mass does not remain constant. It was proved by Einstein, okay. So it increases, the mass needs to increase. It was observed that the mass of the particle does not remain constant, but it increases with increase in velocity. According to the relation m equals to m naught under root 1 minus bracket open v upon c whole square, v upon c whole square. Yeah, this one, I am talking about this one. So where m naught here, m naught is the mass of the particle when it is at rest, right. In such a case we cannot write del m equals to m del v, then del will come in front of m also. The relation del mp is only true if the velocity v of the moving particle is much smaller than the velocity of light. That means here if the velocity of the particle is very small, then c. Now what is c? The maximum value of velocity. Okay, it happens when the velocity of the particle is of the order 10 to the power 6 meter per second or less than this, then the variation in the mass with the velocity is small enough and the mass can be considered to be constant. However, the relation del p equals to del mv is always true whether mass m varies or it remains constant, because change in momentum is because of change in mass or change in velocity or both, right. So the next topic is rate of change of momentum. So first thing we studied momentum, linear momentum, then we studied change in momentum. Now we are studying the third topic, rate of change of momentum, step by step, right. Momentum, change in momentum, now rate of change of momentum. So what is the meaning of rate of change of momentum? It means that when a body is moving, right, and it will have some momentum, right. Suppose we apply a force on it and the body slows down, then the momentum decreases, right, or it might increase also. So in both the cases, whether the body's speed increases or decreases, momentum changes. Now to change that momentum, that body needs some time to change the momentum, right. If the change in momentum is fast, if it takes less time, so rate of change of momentum is more, and if it takes more time, if the change is very slow, then rate of change of momentum is less. So rate of change of momentum means how fast the momentum or how slowly the momentum is changing. So when a force is applied on a moving body, its velocity changes. Due to change in the velocity of the body, momentum also changes. Let a force F be applied on a body of mass m for time t, due to which its velocity changes from u to v. Then initial momentum of a body is mu, final momentum of the body is mv. So change in momentum should be mv minus mu. M is taken out common here, m is taken out common here. I hope you are understanding this. Originally there is a body, okay, originally there is a body, I am writing on top of it. I hope you will not have any problem. If you have any problem, then please let me know in the comment section, right. I am using a different color now, green. So suppose there is a body, okay, suppose I am considering a body, let that body have mass m, right, and suppose force is applied on the body, right, suppose force is applied on the body, and because of this force the body starts moving, okay, and the same body reaches here, suppose, right, same body reaches here without changing its mass, okay. When the body was already moving, let its velocity be u. So in this case its momentum will be mu, right, whereas its momentum at this stage, at the second stage, at this stage will be m into v, right. Suppose this is p1 and suppose this is p2. So what happens here is we have different momentums, right, like here it is written mv, mu, here it is written mv, right. I hope you understood this. Now change in momentum, this change in momentum of a body in time t, so change in momentum and it takes time t will be mv minus mu, the higher value minus the smaller value, right. And here what they have taken, what they have done is they have taken the m common, there are two m's here, and they have taken the m common and it will be m bracket open v minus u. So the rate of change of momentum, this is just change till here, is just change in momentum, right. Now the rate of change of momentum, rate of change of momentum will be equal to change in momentum by time, like rate of change of distance was distance by time, rate of change of displacement was displacement of by time, and the rate of change of velocity was velocity by time. Similarly, the rate of change of momentum will be change in momentum upon time. So, change in momentum's formula will be m v minus u upon t, m v minus u upon t. Now, you know that acceleration is v minus u upon t. You know this relation, right? A equals to v minus u upon t. You know this relationship, a equals to v minus u upon t. Then replacing the value of v minus u upon t by a, you will get rate of change of momentum equals to mass into acceleration. Please remember this, we need it afterwards, right, to while understanding Newton's second law of motion, right, because you all know this force formula is mass into acceleration, and change in momentum's formula is also mass into acceleration. These two should be equal, we will prove it afterwards, right. So now this relation holds true when mass of the body remains constant. Thus, when a force acts on a body, the rate of change of momentum is equal to the product of mass and velocity, mass of the body in acceleration produced in it due to the force, provided that the mass of the body remains constant. So, remember that F equals to m into a is only when the mass of the body remains constant. Okay, there is an alternative method also. This is a simple way, right? mv minus mvu, etc. I hope you understood this. So, the alternative method is using the del. So, you all know this change in momentum is m into v. So, and the change in momentum is del m bracket open mv of mv, right. So, here you can see change rate of change of momentum should be equals to change in momentum by time. So, if here what does not change, a mass cannot change. So, therefore, there is no del in front of mass and will be del v by del t. So, if mass remains constant, again if the mass remains constant. So, but del v by del t is acceleration, because change in velocity by time is acceleration, change in velocity by time. So, it's supposed to be acceleration, right, this one, sorry, this one here, change in velocity by time should be acceleration. So, the rate of change of momentum should be mass into acceleration. I think this method is quite complicated. You can use this method, the earlier one, which is quite easier, right. Okay. So, this much for today, right. The Newton's second law of motion I shall deal in the next video.